All right, so you missed lesson 6.1.1, Barely Alive. In this lesson, we introduced some new vocabulary, possibly new, I should say, and one of the big terms that we're learning about is what exactly is a solution? Well, as you can see here, it's a mixture of two or more substances that is uniform or the same throughout. The substance that's in the greatest amount is called the solvent, and the thing that's dissolved in the solvent is called the solute. So a lot of times, for example, water is the solvent. The ocean is a great example. There's a lot of solute, aka salt, dissolved in the solvent, which is water in this case. Concentration is the amount of solute for a specified amount of solution. So we call this the molarity. It's the moles of solute per liter of solution. Moles per liter most often is written just as a capital M. So basically, the higher the concentration, that means there's more solute and you're going to have a larger molarity value. And finally, homogeneous and heterogeneous, sometimes called homogeneous and heterogeneous. Basically, a solution is a homogeneous mixture, and a heterogeneous mixture is something that's not uniform throughout. So, for example, salsa would be heterogeneous because there's different chunks of tomatoes and jalapeno pepper, versus ocean water is the same throughout. There's a lot of different things dissolved in the ocean, but it's uniform. So as a little introduction, I pointed out these two beakers. I said one of these contains a very dilute, which means it's basically pure water, solution of sulfuric acid. The other one is very concentrated and harmful. Can you tell which is which? And you definitely can't in this picture. They look exactly the same. So, a little bit more terminology. If there's a lot of solute dissolved, we call it concentrated. And if there's just a little solute dissolved, we call it dilute. But those are very general terms. So how do you know how concentrated or exactly how dilute a solution is? So that's where that new term molarity comes in. That's how many moles of solute are dissolved in 1 liter of solution. And remember, a mole is 6.02 times 10 to the 23rd molecules. So, or of anything that you're talking about. So back to the question about could you tell the beakers apart? Going up to this, the beaker on the left is actually 18 molar sulfuric acid, and the one on the right is only 0.1 molar solution. So what that means is the one on the left has 18 moles, or 18 times 6.02 times 10 to the 23rd molecules dissolved in 1 liter of solution, while the beaker on the right only has 0.1 moles of molecules, 0.1 times 6.02 times 10 to the 23rd molecules dissolved in 1 liter of water to make that solution. So if we could zoom in really closely to see how many particles there are for a relative amount. So let's keep the amount the same. It says, what if this one on the left is the 0.1 molar solution, and on the right it wants you to draw the 18 molar solution? Well, this one is going to have a lot more solute packed in. So I'm just going to draw a lot of dots. Technically, I could do the math here, but it says don't do it. I could count on the left side that there's 12 dots, and this is 180 times more concentrated. So I'd have to do 180 times 12 and draw that many dots. So the point is there's a lot more solute packed in there. Okay, so then we did a little activity where we looked at some gummy bears that have been soaking in some different solutions. We had pure water, 0.1 moles per liter sugar, 0.5 moles per liter sugar, 1 mole per liter sugar, 2 moles per liter sugar, and corn syrup, which is higher than 2.0 molar sugar. So what we noticed was the gummy bear in the water is gigantic. Too bad you missed out. You can do this at home though. Just put a gummy bear in water and look at it the next morning. Let it soak overnight. And it just kind of went down from there. This one was also really big. We'll call it large, medium, small. So it says rank the bears with 6 being the largest. It went 6, 5, 4, 3, 2, 1. Then we answered some questions to address what is going on. So first question says, what does it mean when chemists say that a 1 molar solution is more concentrated than a 0.1 molar solution? So the 1.0 molar solution equals 1.0 moles of solute are dissolved in 1 liter of solution. A 0.1 molar solution is only 0.1 moles, so a tenth as many solute are dissolved in 1 liter of solution. There we go. So the more there is, this one would be more concentrated. That's the correct terminology that goes with that. How did the size of the gummy bear relate to the concentration? So the larger the concentration, the corn sugar was the biggest, the smaller the bear. And it says the gummy bear itself can be thought of as a sugar solution. What do you think the molarity of sugar is in the gummy bear? Well, the gummy bear still grew bigger in the 2 molar sugar solution. So you kind of have to take a guess here. Maybe a 3 molar solution? It would be the solution where the gummy bear would stay the same size. So here's my little gummy bear. Draw just a quick picture. If he's in a big solution and the concentration of sugar outside is the same as the gummy bear itself, then the gummy bear will not grow or shrink. But that moves us into our making sense question. When there's a higher molarity outside the bear than inside, that means water from the inside of the bear will rush out to try and help the outer concentration. It says, oh my goodness, we've got to help you out, evenly distribute this water. On the other hand, when you have something that's highly densely packed with sugar, and example, the 0.1 molar sugar solution, there was definitely more sugar concentrated in the bear, water from the outside will rush in to try and distribute that sugar throughout the solution as a whole, and so the gummy bear will grow. So this should sound familiar to you. It's all about osmosis. Water molecules moving from an area of low solute concentration to an area of high solute concentration. Let's move on to some of the math. So, for example, it says, what if you've got 5 moles of table salt dissolved in 10 liters of water in the ocean? What is the molarity? Well, again, we're going to divide the moles by the total volume in liters. So 5 moles divided by 10 liters is 0.5. Okay, good. I can still draw, even with the interruption. So let's do a few more examples here. What about the concentration if you've got 2 moles of glucose in 4 liters of solution. Oh, it's just like the example problem here. 2 divided by 4, that's 0.5 molar. What if it doesn't give you liters, but it gives you milliliters? There are 1,000 milliliters in 1 liter. So we've got to divide by 1,000 here to get this into liters before we can solve the problem. So for number 2, we're going to do 0.8 moles divided by 0.4 liters, and that comes out to be 2 molar. Again, the capital M always stands for moles per liter, but chemists like to do things the easy way, so they found a way to make that shorter. What if you're not given moles? So this is a throwback. What if you're given grams and you're expected to convert it into moles before you solve the molarity problem? So for example, if you dissolve 20 grams of NaCl in 2 liters of water, well, first you've got to take 20 grams and divide by its molar mass to figure out how many moles of that substance is it. Then you can go ahead and finish and do the moles divided by liters to figure out the concentration. So let's do this. What if you've got 225 grams of sugar, C6H12O6? Always start by writing what you know. I want to figure out how many grams, using the periodic table, would 1 mole of C6H12O6 weigh. So I'm going to go off to the side and I'm going to do the math. 6 times carbon's molar mass is 12.01 plus there's 12 hydrogens. They each weigh 1.01 grams per mole. Plus there's 6 oxygen. They each weigh 16 grams per mole. And that comes out to be a grand total of about 180.156 with the periodic table I was using. Multiply across the top and divide by the bottom. We've got 1.25 moles of glucose, and we're dissolving that in 3 liters of solution, it says. So I get a concentration of 0.42 moles per liter. Capital M for molarity. Let's do another one. 249 grams of Ki. We've got to get that into moles. Well, 1 mole of potassium iodide, I've got to go to my periodic table and add that up. It's 166 grams. Multiply across the top and divide by the bottom. That's 1.5 moles of Ki. Divided by, I'm going to first do my 500 milliliters divided by 1,000 to get it into liters. So now I can divide by 0.5 liters, and this comes out to be 3 molar solution. Another helpful thing is the molarity triangle. So to use this, you cover up what you're looking for. So if you want to solve a problem for molarity, you can see what's left over here is moles divided by liters. If you want to solve a problem for moles, you're going to do molarity times liters. And if you want to solve a problem for liters, you're going to do moles divided by molarity. So let's take a look at some example problems here. How many moles of MgCl2 would you need if you want to make 5 liters of a 1.5 molar solution? You can also see how units cancel out. So you want to make 5 liters, and you want it to have 1.5 moles for every 1 liter. So how many moles do you need if you want to make that 5 liters? So we're going to need to multiply those to get our answer. Sample problem B is similar, only there's one extra step. So same way to start. It says you want to make 3 liters, and you want it to have 0.75 moles of this lithium bromide for every 1 liter. So if you want 3 liters, you actually are going to need 2.25 moles of lithium bromide. Well, what does that mean in grams? You got to use your periodic table. Every 1 mole of lithium bromide weighs 86 grams about. So if you need 2.25 moles, we've got to multiply. So I get my final answer there of 195 grams. Now there's a little bit of a different twist in this last one. It's asking you for liters ultimately. It says you've got a 250 gram sample of Ki and you want to ultimately make a 2 molar solution. So how many liters of water do you have to add to that many moles so that it's 2 moles per liter? Well, first figure out how many moles you've got. 1.5 moles. If you want this to be a 2 liter solution, you can do this problem in another way too. 1.5 divided by what is equal to that 2 molar solution? Or you can use your molarity triangle. If you want to figure out liters, cover it up, you've got to do moles divided by molarity. So that's exactly what we did here. Moles divided by the molarity that you want, because you can see your units will cancel out. 1.5 moles divided by 2 moles per liter. The trick is these flip, so it's the same thing as multiplying by liters over moles when you move that bottom part up to the top. So then you ultimately get liters. Let's do a few last example problems here. How many moles of LiF would you need if you want to make a 2.5 molar solution and you want to make 1.5 liters of it? Well, 2.5 capital M is the same as 2.5 moles for 1 liter. If you want to make 1.5 liters, you're going to need some more moles. You're going to need 3.75 moles of LiF. Next problem says, how many liters of a 2.5 molar solution can you make if you've got 6 moles of sodium carbonate? Okay, again, you want to make a 2.5 moles per every 1 liter, and you want to know if you've got 6 moles, how many liters do you have to add to that? So another way you can think of this is you can do 6 moles divided by how many liters will give you that 2.5 molar solution. Well, if you look back at the molarity triangle, you can do this too. If you want to solve for liters like this problem is asking, then you have to do moles divided by molarity. So if we do the 6 moles divided by the 2.5 molar solution, we find out that we are going to need 2.4 liters of the sodium carbonate. And just as an aside, sodium has a +1 charge, carbonate a -2, one of the polyatomic ions, so that's Na2CO3. Little blast from the past. What about number 7? You want to make 2 liters, and you want this solution to be 3.5 moles per liter. So let's figure out how many moles you're going to need. So you're going to need, let's see here, 2 liters times 3.5. That makes 7 moles. And then we've got calcium chloride here. So we've got to add up the molar mass using the periodic table. How much does 1 mole of calcium chloride weigh? So calcium is 40.08. Each chlorine is 35.45, and there's 2 of them. That comes out to be 110.98 grams. Multiply by the 7, and I get 776.86 grams. That's how much calcium chloride I'm going to need to make that 3.5 molar solution. And the last one, what if you've got 100 grams of KNO3? How many liters of a 5 molar solution can you make? Well, I know I'm going to have to get grams into moles. That's pretty much a given for these problems because we're dealing with molarity. So first step, I'm going to convert my KNO3 and see how many moles of it I have. So using the periodic table, I'm adding up 1 potassium, 1 nitrogen, and 3 oxygens. That adds to 101.11 grams. That means I've got 0.99 moles. And ultimately, I want to know how many liters do I need to make a 5 molar solution. So I'm going to flip-flop those. I'm going to take 0.99 moles divided by that 5 moles per liter. 5 capital M. I could have written it like that too. This comes out to be 0.2 liters. And then there are a couple extra questions here for early finishers, so I'll write these answers if you want to do a little extra practice. This one comes out to be 8.75 moles of strontium nitrate, and number 10 comes out to be 149.89 grams of sodium iodine. So you can test yourself on those. All right, hopefully that helps. It was definitely a lot of math, and it's going to be fun to do all the labs where we use the math.